Okay, so today we're looking at surds and how to work with them. So various operations like adding, subtracting, timesing, dividing. Now, what are surds? Surds are numbers where you've got a square root sign, and under that you've got a whole number, an integer, but one such that what you get if you were to look at the decimal values is it would be irrational, meaning it would go on forever without a pattern. And one thing that I think is kind of interesting with surds is apparently the name comes from, it's similar to the word absurd, right? Like something's absurd, because the ancient Greeks thought that they couldn't exist, thought that irrational numbers that went on forever without a pattern couldn't exist. So I think that's kind of fun. But first, so let's look at with surds, how to simplify them. So if you want to simplify a surd, the most efficient way is to split up whatever your surd is into the biggest factor that's a perfect square. That'll get you there the quickest. You can also do it more slowly by just by splitting up into factors that might not be necessarily the biggest one. But so if we look at the square root of 32, some of its factors, 2 and 16, 2 times 16 is 32, right? So pretty reasonably, this root 32 is the same as the square root of 16 times the square root of 2, yeah? Now, the square root of 16 is just 4, since 4 squared equals 16. So then you're left with, well, 4 times root 2 or 4 root 2, as we'd say a bit more simply. So let's have a go at a couple of practice ones. So we've got here root 18. If I think about root 18, well, to me, a perfect square that comes to mind is the square root of 9. Yeah? So 9 times 2 is 18. The square root of 9 is 3, since 3 squared is 9. And so now we simplified it. If you think about 2, it's the only factors it has are 1 and 2, neither of which are perfect squares. So we can leave it there. This one, root 400, funnily enough, I can think of 2 factors, root 4 and root 100. If you were to times them together, you would get 400, right? 4 times 100. And both of those are perfect squares. So we've got 2 times 10. So that one can actually be evaluated as 20. You might have also realized, wait a second, isn't 20 squared 400? And yeah, it is. So if you realize that straight away, you could just skip the whole thing of splitting it up into 2. But yeah, there we have it. All right. We've got a bit more simplifying to do here. We've got 6 root 45. So again, we've got to think about, well, how can I make that any perfect squares in there? As it happens, 9 times 5 is 45. So we've got square root of 9 can be simplified to just be 3. So we've got 6 times 3 times root 5. So you just leave that on the end there. And 6 times 3, what's that? That's 18. So we've got 18 root 5. And that's as simplified as we can go. 5 is a prime number. There's not going to be any more factors. Now, root 72 on 3, it might be easier if you're simplifying this. You could just bring the third out the front, right? That's still the same, right? 1/3 times the square root of 72 is the same as the thing on the left. And then just deal with the root 72. Now, depends how good you are with knowing your perfect squares. Maybe you'd go, oh, I can't really think of any really big ones that go into 72. What if I just do, say, 4? I reckon 4 would go into 72. You just do a little bit of simple division. So 4 into 7 goes once, 3 left over. 4 into 32 goes 8 times. So then I get, so root 4 times root 18 is allowed. That would split up 72. Actually, I did root 18 just above, didn't I? So what was that? That was 3 root 2. So I could simplify some more as well. So really what I've got is, well, root 4, that's really 2. So times 2. And then root 18 is 3 root 2. So now I just kind of times all these things together. And I notice actually my third and this 3 are going to cancel. So I get 2 root 2. That's my answer. All right. So that is simplifying, just a matter of finding perfect squares that are factors of the numbers under the square root sign. Now, with adding and subtracting, I think really with surds, they might seem a bit unfamiliar, but they're quite similar to just if you're comfortable working with algebra, things like X, Y, Z, those kind of pronumerals, it's fairly similar with surds. So the kind of rule is that you can only simplify surds using addition and subtraction if they're what we call like surds. To be a like surd, it just has to have the same number under the square root sign. And the best way to know that they're like surds is if you simplify them, make them use those perfect squares to simplify them down before adding and subtracting them, then you'll know for sure that they're like surds, right? If you've simplified them as much as they can. So let's have a go at these practice ones. So first, 5 plus 4 root 5. So when I was saying about how it's kind of similar to algebra, if I had x plus 4x, you'd probably feel pretty comfortable telling me, oh, well, that's 5x, right? Well, it's kind of the same. It's just x is now root 5. So it's 1 lot of root 5 plus 4 lots of root 5. So I must have 5 lots of root 5, yeah? An implied 1 in front of this, isn't there? 1 times root 5, yeah? So then similarly, right, we got root x plus 2 root x. So that's just 3 lots of root x, isn't it? So really pretty similar to regular algebra, especially nice when you've got, if you've got like surds without having to do any simplifying, that's nice. Here we've got, what, 10 root 2 take 12 root 2. So that'll end up with negative 2 root 2. And then here we've got root 4 plus 4 root 5. And seeing as the thing under the square root sign is different, we can just say that this can't be simplified. All right. Let's go to another example. So this one, a bit more complicated. And so this is where my advice about, well, best to simplify the surds first. That's going to save you lots of trouble. Do that first and then do the addition or subtraction. So here we've got 5 root 18. So that's 5, make the root 18 root 9 root 2 plus root 3 root 100, take 2 root 3. So this becomes, well, root 9 is 3. So we're going to have 5 times 3 here. So it's 15 root 2. And here we've got, well, root 100 is 10. And root 3 can't be simplified. So we just put that on the end. 10 times root 3. And take 2 root 3. So what do we get? The only like surds we've got are these root 3s. So we can simplify them. This 15 root 2 just stays as is. So we get what? 15 plus 8 root 3. Very good. Okay, some rules for multiplying and dividing surds and squaring them. So squaring a square root sign, hopefully quite reasonably, if you square something with a square root sign around it, so the square root of 6 squared is just 6, all right? So it's like the square cancels out the square root. Hopefully that's pretty reasonable. If you think about, writing that out, so root 6 squared is just root 6 times root 6, so you end up with 6, yeah? So as a rule, just anything, if you've got something A under a square root sign and you square it, you just get back the thing under the square root sign, A. So these examples, hopefully pretty reasonable. If you do root 23 all squared, you just get 23. If you do root xy all squared, you just get xy. Hopefully you can convince yourself that that's true. Maybe just play around with some examples if you don't think that is reasonable. Okay. With multiplying and dividing, funnily enough, I think it's probably a bit easier than adding and subtracting because with surds, you can always multiply and divide them. We've kind of been using the fact that you can multiply them to simplify them, right? So if I have root 3 times root 4, you just multiply the numbers under the square root sign, you get root 12. Of course, root 4 is actually 2, isn't it? So a bit of a silly example there. But if you have root 60 divided by root 10, then you'll get 60 on 10 all under a square root sign. So you'll end up with just 6. So as a formula, just multiply the things that are under the square root signs. Or if you're dividing, just make it a fraction, all under one big square root sign. So let's do some examples. So 2 root 6 divided by 3. So it's the same as 2 root 6 over 3, which is 6 on 3 is just 2. So it's 2 root 2. This one, all right, so we're multiplying. We've got coefficients to these surds. So we just multiply the coefficients and we multiply the things under the square root sign separately. So 5 times 3 is 15. So it's us dealing with the coefficients. And then 2 times 7 is 14. So we get 15 root 14. you've got a fraction times the square root, and we can just put it on top. 2 root 3 on 11, just like a regular fraction, you're just multiplying the numerators. If you think about it, root 3 is really root 3 over 1 as a fraction, isn't it? Seeing as we haven't written a denominator. Okay, and that's it. I hope that was helpful for you.